Okay, today we will talk about how to arrange your design if you want to consider interaction. As I mentioned in the last week, that due to fractional factorial, that your design of experiment might result in confounding of some effects, such as main effects and interaction effects. According their confounding situation, we define three types of resolutions. For instance, if you have 4 control factors and you want to put it in L8, and this is L8, and you assign A to column 1, B column 2, C, D to column 3 and 4. Therefore, you can get the confounding structure from the interaction table. We have made this practice before. So first, you need to find out how many two-factor interaction we need to consider. Since there are 4 control factors, A, B, C, D. Therefore, for two-factor interaction, there will be combination 4 by 2, which means that you need to find out 6 two-factors interaction. It should be very straightforward. We usually start from A, B, and A, C, A, D. After finish A, then you start from B, BC, BD, and continue to C, CD. Therefore, you can find out all 6 two-factor interaction. You need to use interaction table. Try to find out where these interactions will be. Which column will it happen in the orthogonal array? So here, for instance, A and B. A in column 1, B in column 2. So look here, column 1 and 2, you can see interaction AB will happen in column 3. So you write AB here. Same thing. For instance, AD will be column 1 and column 4. AD will happen interaction in column 5. So it will be here. Continue from here. So you see this is column 5, column 3, etc. You can find out all the columns for these two-factor interactions and come up with confounding structure. Okay, we do this exercise before, and I will let you do by yourself. You should be able to find out this confounding structure, which means that where are the main effects and where are the two-factor interaction will be in the orthogonal array. So you can see in column 1, factor A and the interaction BC will be confounded, will be mixed together, which means that when you analyze the effect of A, that will be affected by, will be influenced by interaction BC. Same thing. But for AD, interaction AD, which is very fortunately, AD happened in column 5. AD doesn't confound with any other main effects. So AD, BD, and CD can be analyzed if you want to analyze how strong the interaction will be. However, for these 3 interactions, you cannot analyze the strength of their interaction because your analyze will be confounded with the main effect A, B, C. So remember in the last week, we draw the interaction plot, right? And in this case, you can draw the interaction plot for these 3, but you cannot draw the interaction plot for BC, AC, and AB because they cannot be estimated, right? So here we can see, we can have a conclusion that BC, AC, AB cannot be analyzed because they are confounded. But these three interactions can be analyzed using the interaction plot. Okay, this is very important. And in this case, some manifest confounded with the two-way interactions. We call this resolution is type 3, resolution 3. If main effect and the interaction effects are confounded together, we call the resolution is 3. Any questions? Resolution 3. How about this one? This is another layout. Again, we still have 4 control factors, but this time we arrange them in different columns, 1, 2, 4, and 7. So we put A, B, C, D here. Different arrangement will have different confounding structure. We can do the same thing. Try to find out where are these two-way interaction will be in the L8 orthogonal array. So again, if you use the same table in the last page, you should be able to find out the confounding structure like this. And this confounding structure is different from our previous one. What is the main difference? Here, main effects are independent, right? No confounding for main effects. However, two-way interaction, they are confounded to each other. So in case your confounding structure looks like that, which means that all main effects can be estimated because all the main effects has no confounding with any other two-way interactions. But two-way interactions confounded with each other, which means that if you want to analyze AB, CD must be negligible, which means very small. Otherwise, these two interactions confounding to each other. So when you analyze the interaction plot for AB, actually it will be influenced by interaction CD. So in this case, you can only analyze one of the confounded two-way interactions. So in this case, we call this resolution 4. So this is the design resolution. We show 2 examples. Design resolution 3, two-way interaction confounded with main effect. But main effect are independent. Main effect didn't confound with each other. We call this resolution 3. And the resolution 4, two-way interactions confounded with each other. But main effects doesn't confound it with any other two-way interaction. This will be resolution 4. How about resolution 5? Which means that main effects and two-way interaction are all independent. Each main effects will have one column to assign, and each two-way interaction will have independent column to assign. There will be no confounding. In that case, this is called resolution 5. And the Taguchi orthogonal array, he can let you assign each main effect to each column. Therefore, all the orthogonal array will have at least resolution 3. Because you will not assign 2 vectors to one same column, right? So you will have at least resolution 3. So if you want to estimate interaction, either you need to use resolution 5, or you can try 3 or 4. Actually, 3 is not a good idea. If it is resolution 3, then main effect might confound it with some other interactions. However, just like what I said, if your confounding structure, all right, in your confounding structure, if this interaction confounded with each other, but you know that only one is significant. Significant means important, or the inference is large. And the rest of the interactions are negligible, which means they're very small. Then you can use this column to estimate one of the interactions. Or in resolution 3, in the example we just talked about that, here, these 3 can be estimated, but these 3 cannot be estimated since they are confounded with the main effects. Okay, if this interaction cannot be neglected, are not negligible, or if these interactions are very strong, then the main effects will be affected, which means that the determinant of the main effects, which level is good, will be incorrect because they are influenced by some other interaction. This is the conclusion here. Okay, if interactions are negligible, then control factors can be assigned to the linear, or I should say that in our first few weeks, we didn't talk about any interaction. We mentioned that we can use factor and put it in any columns. But from our last 2 examples, we can see the confounding structure will be different if you put your factors to different columns. So if you already know that interactions are negligible, no interaction need to be considered, then you can arrange your control factors to any column. Then it will make no difference because all the interactions are negligible. So that's why at the beginning, Taguchi usually will assume there are no interaction. If there are no interaction, you can assign your factors to any column. Okay, let's try some other example. This is, okay, not an example, this is a summary from previous 2 cases. The first case, 1, 2, 3, 4, assign A, B, C, D. And you can see it is resolution 3. And here, main effect confounding with BC. So we can have a good estimate of A only if BC is negligible. See? Since A and BC are confounded if you make this arrangement. Same thing for B and C. They are confounded with some interactions. All right. Another layout, we put A, B, C, D in column 1, 2, 4, and 7. This will result in different confounding structure. We call it resolution 4. And here, all the main effects are independent. They don't confound it with any other interactions. However, two-way interactions are confounded with each other. Therefore, if you want to analyze the two-way interaction, one of the interaction must be negligible. Or you should say only one interaction can be analyzed. You need to make sure that which one is important. What others are neglected, can be neglected. You have to know that in advance before you do the analysis. So if you want to arrange your factors to the orthogonal array, you must first know the confounding structure. And then you can arrange your factors to the certain columns, and you can see which interaction can be analyzed and which cannot, right? So how do you have the confounding structure? You can use the interaction table, just like what we did. So the design resolution can be determined from the confounding structure. So you first need to analyze the confounding structure. Then you can determine what is the design resolution for your arrangement. So just like here, as we talked about this before, and I mentioned that already, this is an arrangement if you put A, B, C, D in 1, 2, 4, 7, and the resolution will be 4. So here, if one of the confounded interactions are negligible, the other become estimatable, which means that, for instance, here, these two are confounded to each other. So A, B, and C, D cannot be analyzed at the same time. Only one can be analyzed. So you need to make sure, if you understand, if you already know which one can be neglected. But you cannot say, okay, I want to neglect this one. No, you have to analyze from their theoretical background. For instance, say, if you want to analyze what is the inference for your midterm score, we can do an experiment, right? I can assign several factors. Say one of the factors is how much time you spend in watching a video, okay? And how good do you come up the mind map? Or say, what is your performance in the pre-class quiz? There are several factors. Okay, so or I can put another factor, say, what is the color of your shirt? Well, you will know that the color of your shirt shouldn't have anything to do with your midterm score. So you will know that the color of your shirt will not have any interaction with, say, how much time you spend in watching the video. So you know these two factors will be independent. But sometimes you, from the analysis, you will find out that these factors will have some interaction. As I mentioned, so we have 4 factors, maybe more, such as, okay, maybe practice of Excel example. Okay, these are 5 factors that might affect your midterm score. A, B, C, D, E. And if I make it 2 level, for instance, if I make it 2 level and say below 2 hours, above or 2 to 4 hours, 2 level, quality of your mind map, very good or not good, such as you just using AI to generate the mind map. You didn't really pay attention to draw the mind map. And the score of the quiz, we have 4 points, right? Before quiz and the pre-class quiz. These are all your performance. And the last one is the practice of Excel. Did you practice your Excel or not? You want to analyze how these 5 factors affect your midterm score. And if you want to also analyze the interactions. So some of them might have interaction. For instance, these 2 might have interaction, right? How much time you watch the videotape might affect the quality of the mind map. These 2 might have the interaction because when you spend more time in watching videotape, sometimes your quality of mind map will be better. So these 2 have some interaction. But for instance, E, did you practice your Excel or not? And B, how is your quality of mind map? Probably doesn't have much interaction. Since these 2 are quite independent, but because when you draw the mind map, basically just want to understand what is the knowledge structure in this chapter, whether you practice or not, probably will not affect the quality of your mind map. So you will see these 2, B, E, may be negligible. So this is from the actual analyze. Okay, doesn't mean that you can assign randomly by yourself. So if you already know that, just like that one, if you already know that CD is negligible, then AB can be estimated. Okay, so this is estimability, whether this interaction can be estimated. So if you want to set up your experiment, including interactions, then you need to find out which interactions can be neglected. And if you already know that some of the interactions are very important, cannot be neglected, you need to make sure that in the confounding structure, that interaction is in one column by itself, or it is confounded with some other negligible interactions. So basically, we need to carefully assign the factors to the columns to avoid the confounding of main effects and the significant interaction. That is the reason that we need to understand their confounding structure in order to assign our factors to the columns in the orthogonal array. So remember, in the midterm, I ask you that which columns you want to put in your orthogonal array, because it will be very important in our if interaction is one of the considered effect. So if you want to do the analysis, you want to assign the factors to the orthogonal array, but at the same time, we need to consider interactions. How do we do? Either we can use confounding structure, but you can see it will take a long time. You need to assign first and find out that whether your main effects and the significant interactions have any confounding. If you find out that there are some confounding for your main effects and significant interactions, you need to reassign your factors. Therefore, Takuchi proposed a very simple method called linear graph. So what is the linear graph? Linear graph is a very simple method that Takuchi proposed. So you can assign your factors and important interactions at the same time. And to make sure that your main effects and the significant interactions can be estimated, which means that they will not be confounded. This is one of the example of L8. He proposed the common linear graph for each orthogonal array. But some orthogonal array doesn't have a linear graph. I will show you later. All right, this is for L8. And here, he proposed two types of linear graph. For linear graph, they have dot or have line. Dot means you can assign main effect or control factors to the dot. And line means that if these two control factors has interactions, that interaction can be analyzed in column 3. Since column 3 is a line, you will not assign main effects to the line, which means that the main effects will not confounding with these interactions. So basically, assign main effect to point, assign important interaction to the line. So here, we can compare this linear graph with the interaction table. You can find out these are compatible, okay? And this linear graph is only one or two of the special case you can come up from the interaction table. Let's look at the linear graph in the left. As you can see that 1 and 2, right? control factor 1, control factor 2, and the interaction will happen in column 3. You can look at the interaction table here, 1 and 2, so it's 3. So it means that these two are compatible. Again, 1 and 4, factor 1 and factor 4, the interaction happen in column 5. 至于 how about factor 2 and factor, if you assign factor to column 2, another to column 4, where is their interaction? Column 2 and column 4, which column will have their interaction? 6, yes. You can see from the linear graph. You can also see that from the interaction table. 2 and 6, I'm sorry, 4. 2 and 4 in column 6. So these two are compatible. You can see the same situation in another linear graph. But as you can see here in this linear graph, you only consider 3 interactions. Here, you only consider also 3 interactions. But in this case, you can see if you have 1, 2, 3, 4 factors, like this, oh, I erased that. If you have 4 factors, there will be actually 6 interactions effects, which means that you can only estimate 3 out of 6. So how do you use a linear graph to assign the orthogonal array? First, you need to make sure that the experiment is big enough. So you need to calculate the required degree of freedom and to select a suitable orthogonal array. I will talk about what is a degree of freedom. And if you find out the suitable orthogonal array, then you can choose one of the linear graph. So here, you assign factor to the point, and if the interaction is assigned factor to the points, and then the interaction need to happen in the line between 2 factors. If some interaction are in importance, the factor has to be assigned to the dot with some line. If AB is important, AB interaction is important, you need to find a linear graph that A in one dot, B in another dot, but AB will have a line connected with these 2 dots. If the standard linear graph are not enough, we can modify the linear graph. Okay, so let's try to use the linear graph for L8 example. Now you have 4 factors, A, B, C, D, just like a similar example we did that before. And here it tells you that only 2 interactions are important, significant. Significant means strong, important. AD and BD. So you need to, we have 2 orthogonal array. First, I'm sorry, you have 2 linear graph. You first need to select a suitable orthogonal array. So as I mentioned, orthogonal array can be 2 level, 3 level, or mixed level. This is a 2 level, so we need to select a 2 level orthogonal array. So here, since this is an easy example, we tried that before, so we know that we can assign this to L8. Now, how to assign? First, if we assume we select this first linear graph and try to see if we can assign these factors to the linear graph. As I mentioned before, we need to make sure that this interaction will have a line. So usually there's a tip. We assign the factors that happen in the interaction the most, which means that here D appeared 2 times, right? AD, BD 2 times. So we need to assign D first and assign D to the line and to the point with 2 lines, since it has to consider 2 interaction. If here we assign D in column 1, if we assign D in column 1, then because D has 2 lines, then we can assign A and B to the dot that are connected with D. So here, if we assume A in dot 2 and B in dot 4, which is good, since we can make sure that these two interactions will have a position, will have a line to estimate. Once you already assign A, D, B, the rest is factor C. Here we have another dot here in column 7. So you can assign C to dot 7, then you can finish the assignment. And this assignment will make sure that main effects were not confounded with the significant interactions. Or you can try, okay, they are all estimable. Okay, they are all estimable because they don't confound with each other. You can also try the other one. In this case, we can also try this linear graph, okay? We did use this linear graph, but we can also try this linear graph. Why? Because it also has 4 dots, 2 lines. Then we can assign D first. So we can put D here. Which one will you assign first? Which factor will you assign first? Which factor? A, B, C, D. Which one first? D, okay. D in which column? Where? 1, yes. Because if you assign D here, you need to make sure D has at least 2 lines, but it has 3 lines. Okay. What's next? Why do you want to put it 2? Because AD has an interaction. If you put A here, then you can make sure AD is estimable since it will happen in column 3. Okay? Now, 例如, what's the next factor to assign? D, which dot? 4, yes. We can put D here because D has a line connected with dot 1. Then, I'm sorry. So, which factor you say? C? Which one? What's the next factor to assign? B, yes, sorry, B. So we can make sure the interaction BD will happen in column 5 because we need to assign the factors happen in the interactions. Start from D and then A, B. The rest is C. Only C need to be assigned, and C, we have another dot here, so we put C here. So this is a suitable arrangement too. Okay, so you can use either linear graph. In this case, you can either use the linear graph on the left using this assignment, or you can use this assignment. And you can find out these two are the same, right? In this case, these two are the same. D in column 1, A in 2, B in 4, okay, C in 7, the same. All right, and if you look at the confounding structure, this is their confounding structure. What is, remember a resolution? This is resolution 4, right? We mentioned that example before, resolution 4. And here we have 6 two-way interaction. But in this example, he said only these 2 are significant, and the rest are negligible. Negligible means the inference is small. Significant, important. So we only have 2 important interactions, these 2. And the rest 4 interactions are negligible. So even though these 2 are confounded, but okay. This arrangement will make sure AD and BD can be estimated. Why? Because we already know that this and that are negligible. These 2, even though they confounded with the effects we want to analyze, but okay. They are negligible. That is the linear graph. Any questions? This is another example for L16 interaction table. Right? This is interaction table. And you can also find the linear graph. And you will know that L16 is a two-level orthogonal array. Okay? All right. Let's take a 5 minutes break and come back later. All right. Let's continue. So here you can see that this is a linear graph for L16. There are 4 linear graphs. So when you select L16, you need to find out that which linear graph will be suitable. You can always start from how many dots you need and how many lines you need. Here you have 8 main effects, also 8 main effects, but 5 main effects, 7 main effects. So you can see that if you want to analyze more main effects, then you need to sacrifice the interactions. Here, you can only analyze 7 interactions. But if you choose this linear graph, you can analyze 5 main effects, but here you can analyze 10 interactions. So if you want to have more interactions, then you will not have as many main effects. Okay? And this is for 3-level L27, 3-level orthogonal array. As you can see, this is the interaction table. And you can see that the interaction table for any 2 columns, for example, column 1 and column 2, their interaction will happen in column 3 and 4. Any other example are the same. Column 2 and column 4, as you can see, column 2 and 4 here, 2 and 4 happen in 1, 3, 1, 3. Okay, 1, 3. Always happen in 2 columns. So this is the corresponding linear graph. Takuchi proposed 2 linear graphs. Okay, he proposed 2 linear graphs. This linear graph has 1, 2, 3, 4, 5, 6, 7 dots, but 3 lines. This linear graph has 5 dots, but 4 lines. So it depends on how many factors you can choose one of the linear graph. And how do you design your experiment using the linear graph? We already tried some example. Let's practice more. For instance, here, A, B, C, D, and 2 interactions, AD and BD, very similar to our previous one. Other interactions are negligible. So how do you select? Okay, very similar to our previous example. We start from D, right? Because D happened twice. And D has to assign a line, a dot, where has 2 lines. We need to find a dot with 2 lines for D, since we need to analyze AD and BD. Right? So this is our example. We tried that before. And how about another example? This time we have 3 interactions. A, B, C, D, but AD, CD, and BD. So first we need to select which linear graph will be suitable. 4 dot, 3 line, 4 dot, 3 line. Well, it seems this one and that one are okay, are both okay. But you look into the interaction more deeply. AD, CD, BD. So D happened 3 times. 3 times, right? So you need to assign D in the dot. In the dot has 3 lines, because you need to consider 3 interactions, all associated with factor D. then you can see this one is not suitable. This one is better. Since this one has a dot with 3 lines, but this one doesn't. So we select the second linear graph and assign D first to column 1, and then ACB to 2, 4, 7. Then we can make sure that 3 interactions can be estimated, and no interaction and no two-factor interaction and main effects will be confounded. We have 1, 2, 3, 1, 2, 3, 4, 5, 6, 6 3-level factors, and 1, 2, 3 interactions. 6 3-level factors, 3 interactions. How do we assign? First, we need to select a suitable orthogonal array. Okay, so from this orthogonal array table, standard orthogonal array table, we can see we need to find out the one with at least 1, 2, 3, 4, 5, 6 can accommodate 6 3-level interactions. So here, level 2, level 3, and there are some mixed level. Also, there are level 4 and level 5, but not as common. We often use 2-level and 3-level in orthogonal array. So here, 3-level. We need to look at the 3-level, and we need to have 6 3-level factors. So you can see L9, too small. L18 looks good, right? L18 looks good, but L18 cannot be used. Why L18 cannot be used? Because L18 is a special orthogonal array. I mentioned that before. It's a very special orthogonal array that cannot be used to estimate interactions. I will explain that later. So we need to go to the next one, which is L27, which has 13 columns. That will be good for our case. And there's another situation you can consider. As we mentioned before, that A has 2 degrees of freedom, right? 2 degrees of freedom, which means that they have 2 independent variables, A1, A2. And we don't need to find out the main effect A3 because A1, A2, A3, the summation need to be 0. So if a 3-level factor such as A, the main effect A1, A2, A3, actually there are only 2 independent variables. Why there are only 2 independent variables? Because we add another assumption. What assumption? A1 plus A2 plus A3 will be 0, right? We already ate this assumption. Therefore, the main effects only have 2 independent variables. Or we can see the degree of freedom will be 2. I will talk about that again later, but I want to mention it now. And remember the interaction plot? This one? For 2-level, the interaction plot will stand for how strong the interaction will be, right? How do we compare how strong the interaction is for 2-level? We compare these 2 lines, whether they are parallel or not, or we compare 2 values. What 2 values? Remember? We compare this one. We want to determine whether these A, B are has a strong interaction or not, we just need to compare the difference between D2 and D1. If D1, D2 are equal, which means these two lines will be parallel, 平行. If they are parallel, then no interaction. So we just need to compare the difference between D2 and D1, which means that the interaction for two level only need one comparison or only have 1 degree of freedom. We just need one variable. We can conclude whether they are interaction or not. If the difference between D1 and D2 are very small, no interaction. Very big, strong interaction. Okay? How about three level? How about three level? For three level, we have seen this slide before, right? This is three level factors. This is three level interaction plot. If I want to ask you if they are parallel or not, you need to make 4 comparisons. You first need to look at the left because there are 3 line segments here. 1, 2, 3. You need to compare whether these two are parallel or not. And then compare this and that are parallel or not. But you don't need to make the third comparison, compare these 2 lines, because you can conclude from the previous. If these 2 are parallel, these 2 are parallel, then these 2 will be parallel. Okay, so there will be 2 comparisons. On the right, again, there are 3 line segments. You have to make two comparisons to determine whether they are interaction or not. Therefore, you have 4 comparisons in total to determine how strong a 3-level interaction is. So we can also say that there will be 4 independent variables in the 3-level interaction, or we can say the degree of freedom will be 4. Why did I need to talk about this one? Because if a interaction has 4 degree of freedom, in this example, we are talking about L27, but now you have 5 two-level factors. So you can see that you have 5 columns. You need 5 columns, right? And each column will have 2 degrees of freedom because each column can be assigned 3-level factors. But now you have 3 interactions. As you can see that the 3-level interaction need more variables, need more degree of freedom to estimate, which means which is the reason why we said that the interaction of 3-level will occupy 2 columns. You need 2 columns to estimate 1 interaction, right? From the interaction, from the linear graph, we can see you need 2 columns in 3-level. We need 2 columns to estimate 1 3-level interactions. So here, from this example, he said we need to estimate 5 interactions. So we need 5 columns for the main effect, but 3 interactions. Each interaction needs 2 columns. So we need 3 by 2, 6 columns. So which means that in total, we need 11 columns. We need 11 columns if you want to estimate A, B, C, D, E, F, and also 3 interactions. So let's come back to this orthogonal array. You can see that first, L18, it cannot be used to estimate interactions. Even though it can be estimated interaction, it is not enough because it only had 7 3-level columns. And from our estimation, we need 11 columns. We need 11 columns. So how about L27? L27 has 13 columns, which is good enough for our 11 columns, right? Okay, so here you can see L27 is okay since it has 13 columns. Any questions? Okay, so we have two linear graphs. We can select. Now let's look at the interaction first. We need to find the interaction to assign AD, BD, and AB. You can see A happened 2 times, B 2 times, D 2 times. So you need to find out an interaction with 3 dots. Each dot has 2 lines. So this one is no good. This one is okay. Can you understand? Right? Because we need to assign these 3 interactions, A 2 times, A happened 2 times, B happened 2 times, same thing, C happened 2 times. So we need to find out, we can see this one is better, not that one, because this one, you can only find 1 dot with many lines, but we need 3 dots. Each dot has 2 lines, so we select the one in the left. So how to assign? We can assign A first. Once you assign A, D needs to be column 2 or column 5. If you put B here, then D has to be in column 5. So you put A, B, D, make sure these 3 interactions can be estimated. Any questions? Okay, A, B, how about C? C can put in the dot anywhere here. Okay, so you make sure that all these interactions are take care. C put in dot 9 and what else? E in dot number 10. So in this arrangement, you can make sure that all 6 three-level interaction and all 5 three-level factors and the 3 interaction can all be estimated. Next, sometimes, okay, let's try this. Sometimes we can find a linear graph suitable for our purpose, for our need, but sometimes we couldn't. This is one of the example. We have 4 ABCD, 2-level factors, and we need to consider 3 interaction, AD, AC, BD. You can try. You can try by yourself to see if you can arrange this design in the L8. Okay, just like what we did. Let's try A happen 2 times. So how about what others? D happen 2 times. So we need to assign A and D first. A has a place with 2 lines. B has to find out a place with another 2 lines. At first thought, this linear graph seems okay because we have 1, 2, 3, 4 dots. Okay, 4 dots, good. 3 interaction, 3 lines, perfect. But if you take care of this first, we need to assign A and D. Assume you put D here and you put A here. And AD interaction will happen in column 3. And there's an interaction with D, which is B. So we need to put B here. So DB can be estimated. But what's next? Next, you need to assign whether C or B, right? B and C. Next, you need to assign B and C. Now problems. B, let's try C. C has to connect it with A. Well, C has to connect it with A. But the problem is A only have 2 lines. One is used by D, the other one is used by D. Even though this line is good, but you have to assign C into column 4 in such a way that AC can be estimated in column 6. But you can see that column 4 is already occupied, right? So you cannot assign C to here. If you assign C here, it appears AC is good, cool. However, these two will confound. And we cannot confound many facts. So no good. And you will find out that no matter how you try, you will not be able to assign these 3 interactions simultaneously. Why is that? Let's look at your arrangement. You are putting A, B, C, D to 1, 2, 4, 7, right? Since there's only one dot left, so you put C here. But you can see this is no good. Since you put C here, C has no, you cannot estimate the interaction with C. Why? Let's look at the confounding structure. D in column 1, A in column 2, B in column 4, C in column 7. If you come out a confounding structure, you can find out this is resolution 4, right? And the problem is these 3 are significant interaction. These 3 are negligible. But these 2 will be confounded to each other. Since for this arrangement, you only have 4 dots. If you put C here, what happened? You try to analyze AC, right? AC. But where is AC? No line. There's no line here. If you see, well, why not connect a line? If you connect a line here, you can find out AC, column 2 and column 5. The interaction will happen in column 5 as well. Okay? Since there's one dot here, if you put C into here, you can see 2, 7, the interaction will happen in column 5. And here, column 5 already occupied by BD. Okay, if you check the interaction table, 2 and 7, column 2 and 7 will appear in column 5. So you put C in column 7, the interaction in column 5 will confound with BD because BD is already assigned to column 5. You can see from the confounding structure, actually BD and AC are confounded to each other for this arrangement. Therefore, you cannot both estimate BD and AC, which means that L8 in this case cannot be used to satisfy our design requirement. You can try again. You can try by yourself. You can find out that there's no way you can arrange A, B, C, D, and in such a way, these 3 interactions can be estimated. So how can we do? Okay, sorry, there's a table here already. So we can modify or we can expand the linear graph. Okay, I will just go to the modification directly. I will skip the introductions. Because the linear graph are compatible with interaction table. So we can modify some line. If this line doesn't need to be used, we can cancel one of the line and to create more dots. Or you can connect 2 dots. But you need to find out from the confounding structure that these 2 dots will appear in which column. The line will appear in which columns. And you need to make sure that only 1 vectors can be assigned to that columns. So for instance, here, if you have 5 vectors, 2 interactions, this is 2-level example. As you can see that this linear graph is not enough, right? 99, because you only have 4 dots, but you have 5 two-level factors. But only need 2 interactions, but this has 3 lines. Therefore, 1 line will not be used. So you can pull this line out, cancel this line, and create another dot from this line, become this one. So this is a new linear graph. And this linear graph can accommodate 5 main effects, 5 dots, and 2 interactions. So this can be used for this example. Very simple. D appear twice, so D here, A and B here, and the rest of the factors, column 6 and column 7. Any questions? This is one simple modification. If interaction between 2 factors connected with a line is negligible, if you don't use a line, if these 2 interaction is negligible, then you can, these columns assigned to a line can be pulled out, become a new dot. Okay, so become new as dot 7, and you create another dot 6. And now you can safely assign all 5 two-level factors and 2 interactions. Continue. What if you want to connect 2 dots? Can we connect 2 dots to create new interaction? Answer is yes. For instance, like here, there are 5 dots from our previous modification. If you want to consider, okay, if you want to consider 2 and 7, if you want to say, I want to create another interaction here to analyze the interaction between column 2 and column 7. If you want to add another line here, okay, you need to be careful. If you want to add another line here, you need to look at the interaction table to see 2, 7, 2, 7, which column. You will need column 5 to estimate the interactions of 2 and 7. However, 5 is already used in this column. So you need to make a decision whether you want to keep this line or that line. You can only keep one line. So if you want to analyze interaction 2, 7, then you need to remove. You cannot estimate 1, 4. You need to remove this line in order to connect 2, 7. Otherwise, your linear graph will have confounding effects, right? So basically, we want to make sure each number will happen only 1 time. So if you connect 2, 7, there will be another 5 here, so you need to select these 2, okay? And if you keep this one, you have this linear graph. If you keep that one, you have the left linear graph. Any questions? This is a modification you can do. All right, say at the same times, if you want to connect from previous example, if you want to consider the interaction between 2 and 6, there was no line. But if you want to connect it 2 and 6, now again, look at the interaction table here, 2 and 6, 2 and 6. So you can see that for this interaction table, 2, 6 will happen in column 4, right? Column 4, this one. 2, 6 in column 4. So if you want to connect 2, 6, you will need 2, 4, not 2, 6. 2, 4. If you want to connect 2, 4, 2 and 4, it will happen in column 6. So in previous case, column 6 is used in 1 dot. So if you want to consider the interaction here, these 2 can only be selected 1, either this line or that dot. If you want to connect this line, Then you need to cancel that dot here and make a new linear graph like this. This another linear graph. But you can see this linear graph actually is one of the standard linear graph that Taguchi proposed, right? Taguchi proposed two standard linear graphs. One is a triangular one. The other one is one line, one dot with three lines. So you can see that you can modify this linear graph, but you need to make sure they are consistent with the interaction table. How about three level? In three level, you first need to consider how many columns do you need for interactions, three level interaction. They will need two columns. So each three level interaction will need two columns. For instance, our previous example we did here, 6 control factors, 3 interactions. Then you want to select one orthogonal array for your arrangement. How many columns you need? You will need 1, 2, 3, 4, 5, 6. 6 columns. 6 columns for the main effects. And you need to consider 3 interactions. So each interaction will need 2 columns. So you need to find an orthogonal array will have 12 columns or more in order to accommodate these 6 main effects, 3 interactions. So go back to the interaction table, orthogonal array table. You can see L27 is okay. L18 is not enough, not just not enough, but also L18 cannot estimate interactions and also too small, right? L7 only has 7 columns. So we need to select L27 right here. See, 3 level, L18 only 7 columns, but L27, 13 columns. Good, 13 columns. That's 13 columns. So L27 is good enough. But L18, not just too small, but L18 cannot be used to estimate interaction. So we select L27. L27 has 2 linear graphs. Which one do we need? You will find out this example, none of these linear graphs are good because we need 6 dots, 3 lines, right? We need 6 dot, 3 line. So we need 6 dot, 3 line. Neither are good enough. Good enough, okay. 1, 2, 3, 4, 5, 6 dots, okay. 3 line, okay. This is not good enough. 1, 2, 3, 4, 5 dots. So at first you will select this linear graph. But let's look at the interaction again. In this example, this interaction D happened 3 times. D happened 3 times. So we need to have a dot with 3 lines, right? D happened 3 times. We need to have a dot with 3 lines. So this is not good. So we need to use this one. 1 dot with 3 lines. But the problem is, if we are select this linear graph doesn't have enough dot. What do we do? Then we can modify. How do we modify? Because we only need 3 interactions. But here you have 4 lines, which means that one of the lines doesn't need to be used. So we select from here, and from here we know D need to be assigned in this one, all right? D need to be assigned in this one, and A, B, E can be assigned in column 2, 5, 8. However, anyone assigned to column 11, these interactions are negligible. We only have 3 interactions significant. So column 12 and column 13 don't need to be used. Then we can create new dot by putting this line here and become new dot 12 and 13, which make 1, 2, 3, 4, 5, 6, 7 dot. Good, 3 line. Good enough for our design experiment. So here, you just assign D here, ABE 256, 258, and the rest of the factors in column 11 and 12. And you can see we can modify the original linear graph and create more dots by using those unused or negligible interactions. Okay, in this example, since they are all explanation of how do you use linear graph, so we don't have exercise or homework. However, I will suggest you to look at the videotape more carefully, so you will know that how to modify the linear graph or how to understand how to assign your factors to the linear graph. Any other questions? Right? If no, then this is very rare situation. We can see you next week.